Okay, so this is section 1.6, and 1.6 is another section of factoring binomials, and it's titled Factoring Sums and Differences of Cubes. And hopefully you just went through the section on factoring sums and differences of squares, where the sums of squares were prime, the difference of squares factored where you got one parentheses with a plus, one with a minus, you divide the exponent by 2, you take the square root of the number. Cubes are a little bit different in that both sums and differences of cubes factor, and the factoring is more complicated. The factoring actually looks way more complicated than the original problem. So I should talk about what makes something a cube problem. So to be a cube problem, you need to have two terms, just like our squares had to have two terms. Maybe I'll compare squares and cubes. To be a square problem from the last section, you also needed two terms. Here, if I have letters, they have exponents that are multiples of 3. So I could have like an x cubed, or a y to the 6th, or a z to the 9th, or a w to the 12th. In squares, the letters have exponents that are multiples of 3, of 2 should I say. Like we had x squared, y to the 4th, z to the 6th. You notice 6's occur in both. Actually 12's occur in both. There's some problems that are kind of crossover problems that can be considered a cube or a square, and they're a little more advanced than I'd want to do in an introduction to factoring squares and cubes, so we won't really look at those. And in a cube problem, the numbers need to be a perfect cube. And I could do cubes all day on my calculator, so let me show you some cubes. 1 to the 3rd power is 1 cubed. And 1 cubed is equal to 1, so that's a potential number for these problems. 2 to the 3rd power is 8, so that's a perfect cube. 3 to the 3rd power is 27, that's a candidate for a cube problem. 4 to the 3rd power is 64, one of those combination numbers, 64. It's 4 times 4 times 4, so it's a cube. It's also 8 times 8, so it's also a square. 5 cubed is 125. 6 cubed, if I can actually type it, 6 cubed is 216. So the kinds of numbers I need to see in a cube problem are perfect cubes, which is some number cubed. In square problems, the numbers are perfect squares. Like 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, and so forth. So there is the rare candidate that could be both a cube and a square. 64 was another square. This problem right here is kind of a hybrid problem. X to the 6th plus 64, it fits this rule because its exponent's a multiple of 3 and the number's a perfect cube, but it also fits exponent as a multiple of 2, the number has an integer square root. It turns out that's not particularly hard. You can treat it as either, and all these are going to be two-step factoring problems. And again, it's a little more complicated, so I'm going to ignore, I'll call these hybrid problems that can be both a square and a cube simultaneously, and the problems I give will be clearly squares or clearly cubes. So once we can separate something and classify it as a cube, meaning there's two terms, I look at the exponents, I look at the numbers, then we'll separate between differences and sums of cubes, just like we did with squares. And remember, sum of squares were prime, but differences of squares factored, and they had nice looking factoring. You had two identical parentheses, one with a plus sign, one with a minus sign. The contents of the parentheses were more or less the same. With cubes, both cubes with a plus sign and cubes with a minus sign factor. So unlike squares, there aren't any prime cube problems. And unlike squares, the factoring almost looks like it's not worth doing because it looks way more complicated than the original problem. In terms of I'll write down some examples. Of sums of cubes, just so you can know what they look like, and examples of differences of cubes. So they have to have two terms. Exponent needs to be a multiple of 3. The number has to be a perfect cube. So if I look at my exponent, it's a multiple of 3. The number 8 is a perfect cube. That makes it a sum of cubes. If I had like z to the 9th plus 27, that would be a sum of cubes because the exponent's a multiple of 3. The number's a perfect cube. If I had 125 y to the 3rd plus x to the 6th, that fits the definition too. The exponent's a multiple of 3. That exponent's a multiple of 3. The only number I see is a perfect cube. As long as I have two terms, exponent's a multiple of 3, numbers are perfect cubes, it classifies as a sum of cubes. To be a difference of cubes, you could be like x to the 3rd minus 27. Fits my rule, has a minus sign between two terms, exponent's a multiple of 3, numbers a perfect cube. Maybe 125 y to the 6th minus 8. That would also be a difference of cubes. They both factor, and they factor in a kind of awkward way. I'll say this. This is my template for factoring sums of cubes. And again, I'll have to get into the lecture for this to make sense. I'll write this template down. And it looks like a mess, and it is a bit of a mess at first. And here's my template for factoring differences of cubes, because they both factor, neither one is prime. The first parentheses has two terms when you factor cubes. And oddly, the second parentheses when you're factoring a cube has 3 terms, which is very strange. It's the only factoring I know that comes out like this. That's my template. I'm going to talk about how to fill in the template and how to get these things factored. After I do 5 or 6 problems, I think you'll think factoring cubes is easy. Checking is not easy. I'll check a couple of them. I won't check many of them. But the factoring eventually will become easy. The template strategy that I use is nice. So let me get into the problems and explain the details of factoring cubes. So, first problem in this section, y cubed plus 64. That's a sum of cubes. And what I'm going to do first is write why I call this a cube. I call it a cube because y cubed can be written as y times y times y. And something's a cube if it can be written as 3 identical things being multiplied. To figure out how to write 64 as a cube, I'm going to use my calculator and find the cube root of 64. So on my calculator, I'm going to hit the shift key and then the square root key. And that tells me it's going to do the cube root, and I'm going to type the number 64. So I did shift, square root key, typed in 64, and this tells me that 4 times 4 times 4 is 64. So I call this problem a cube problem because each of the pieces, the y cubed and the 64, can be written as three identical terms being multiplied. Now I'm going to yank out my template. My template is going to look like this. The first parenthesis has a plus sign. The second parenthesis first has a minus sign, then has a plus sign. A student of mine many years ago taught me how to know the template signs. The first parenthesis gets the same sign as the original problem. The same sign as plus is plus. The second parenthesis, the first sign in it is opposite of the original problem. Opposite of plus is minus. And the last sign is always plus. And he used, this guy named Juan, nice guy, used the acronym SOP to know his signs. So first parentheses, you get the same sign as the original problem. Second parentheses, opposite from the original problem, opposite of plus is minus, and then plus. Now the easy part, filling in the parentheses. The first parentheses, you get one of each. What do I mean by one of each? One y and one 4. Second parentheses, I'll put these in pairs. First pair is going to go first, y times y. Second pair is going to go second, y times 4. Third pair is going to go last, 4 times 4. I need to do that multiplication. I can't leave the answer like this, but this is going to be the answer. Looks way more complicated than any answer that we've gotten so far, but I'm going to get a y plus 4 in the first parentheses, that's one of each. And now I'm going to multiply my pairs. Y times y is y squared. Y times 4 I'm going to write as 4y. 4 times 4 I'm going to write as 16. It's done. It's all there is to factoring. There's way more to checking than there is to factoring. Let me go ahead and show you that this is the right answer. It's not really fun to check these, but I certainly can check these. To check these, we have to rely on some of the skills we learned in Chapter P. So to check this, I'm going to take my answer and multiply it out. So my answer that I believe is right is y plus 4 times y squared minus 4y plus 16. I'm going to multiply first. I'm going to go y times y squared, which is y cubed, then y times minus 4y, which is minus 4y squared, and then y times positive 16, which is positive 16y. And then I'll start with a 4. I'll go 4 times y squared, which is plus 4y squared. I'm lining it up vertically to make my work easier. Then 4 times minus 4y, which is minus 16y. And then 4 times 16 is positive 64. The y cubed I'll bring down. These are going to cancel, and the 64 I'm going to bring down. So this multiplies out to be y cubed plus 64, and because that's exactly the original problem, I know I've done my answer right. Even though the factoring looks really complicated, more different than what I'm used to seeing in a factored answer, that's considered factored correctly. The nice thing about cubes is other than the signs, I fill up the parentheses the same way, meaning one of each and then pair and multiply. 4 is a difference of cubes. It's a cube problem because the first y cubed can be written as 3 y's being multiplied, and 64 can be written as 3 4's being multiplied. So it's a cube problem. I'm going to get my template. First parentheses gets the same sign as the original problem. The same sign of minus is minus. That's part of my SOP. Second parentheses has 2 signs. The first sign is the opposite sign from my original problem. The opposite of minus is a plus. The third sign, or the second sign in the second parentheses, is always plus. So there's my templates for my signs. It's the same template that I gave a few sheets back. First parentheses, one of each. 1y and 1, 4. Second parentheses, I'm going to start making pairs. First pair, y times y. Second pair, y times 4. Last pair, 4 times 4. First parentheses is going to stay y minus 4. Second parentheses, the y times y, I'm going to make a y squared. The y times 4 I'm going to write as 4y. And the 4 times 4 I'm going to write as 16. That's it. So the thing about cubes is they both factor, and if you can factor sums of cubes, you can factor differences of cubes all day because they factor exactly the same way, except the only difference is the sign. I'll check something that's a little more complicated down the road a little bit. I won't check this yet. 6 is a cube problem, as is 8. For 6, I need to find the cube root of 125. So I'm going to go shift square root to get the cube root and do 125. The cube root of 125 is 5. So this is a cube problem because x cubed can be written as x times x times x, and 125 can be written as 5 times 5 times 5. Now that I've identified it as a cube problem and wrote what makes it a cube, I'm going to get my template. First parentheses has the same sign of plus is plus. The second parentheses, first you get the opposite sign of plus, the opposite of plus is minus, and then the last is always plus. Have my template signs. I know what goes in each parentheses. First parentheses, one of each, which means 1x and 1, 5. And I'm going to pair and multiply. First pair goes first, which is an x times x. Then I put the middle pair, which is x times 5. Then I put the last pair, which is 5 times 5. My answer for this, first parentheses, that x plus 5 is going to stay x plus 5. Second parentheses, x times x is x squared. Minus x times 5 is minus 5x. 5 times 5 is positive 25. Again, I could check that, but I'll save the checking because there's kind of a nuisance to do. 8 is going to look a heck of a lot like 6 because it looks a heck of a lot like 6 to start. It's the same x times x times x and 5 times 5 times 5. The only difference between factoring cubes with pluses and cubes with minuses are the squares. You fill up the parentheses the same ways. The first parentheses with a minus starts off with the same sign as a minus. The same sign of a minus as a minus. And then the second parentheses starts off with the opposite sign of the original problem. The opposite of a minus is a plus. And then they all end up with a plus. Again, we use same, opposite, plus, SOP. First parentheses, one of each, 1x, 1, 5. Second parentheses, first pair, x times x. Second pair, x times 5. Third parentheses, 5 times 5. First parentheses stays put as an x minus 5. Second parentheses, x times x is an x squared. Bring down this plus sign. X times 5 I rewrite as 5x. Bring down the plus sign. 5 times 5 I write as 25. If you look at the answer to 6 and you look at the answer to 8, they look a heck of a lot alike. In fact, they're identical except for signs, and that's the way cubes work. If you have the same cube, then the only difference the minus and the plus make is how the signs fall in the parentheses. Hey, 10 and 12 look remarkably similar. I'm going to change 10 to be y cubed minus 27 because otherwise I'd have two of the same problems. So I'll change that so when you print it out you don't see that. So, template, signs, same sign as minus as a minus. Opposite side of minus is plus, and plus is always plus at the end. Again, it's same, opposite, plus. What makes this a cube? Y cubed is a cube because it's y times y times y. 27, if I do the cube root of 27, I get 3. So 27 is 3 times 3 times 3. First parentheses, one of each, meaning 1y and 1, 3. And then pair, pair, pair. So y times y times 3, 3 times 3. So my answer is going to be y minus 3 for the first parentheses, and then y squared plus 3y plus 9 for my second parentheses. When I go to factor 12, it's going to be the same thing because it has the same numbers, just the signs are going to be different. So the signs are crucial. First, I'm going to get the same sign as 12, which is plus, and then the opposite sign of plus, which is minus, and then the last is always plus. And I'm just going to copy the contents down, and I'll go ahead and check this one to show you that it works. So thinking that making sure I actually checked. Yeah, I checked the plus. I should check the minus one. So first, I'll do this along then. First parentheses, one of each, which means 1y and 1, 3. Second parentheses, first pair is y times y. Second pair is y times 3. Third pair is 3 times 3. So my answer is going to be y plus 3 times y squared minus 3y plus 9. I'm going to go ahead and check number 10 just so you can see one with a minus checked. I don't like checking these, but we should check them every now and then just to show you that we can, even though they're not. I'd never check these because I'm confident in my ability. But if I wanted to check number 10, and I said this is the answer, I'd have to check number 10 by multiplying y minus 3 times y squared plus 3y plus 9. I'll go y times y squared to start and get a y cubed, and then y times 3y and get a plus 3y squared, and then a y times 9 and get a plus 9y. Now I'll start with the minus 3. I'll go minus 3 times y squared and get a minus 3y squared, and then minus 3 times 3y and get a minus 9y, and minus 3 times positive 9 and get a minus 27. The 3y squareds and the 9y's cancel. The y cubed doesn't cancel. The minus 27 doesn't cancel. That equals exactly the original problem, so I know that problem 10 was factored properly. So I could check every single problem. That requires me doing 6 multiplications, lining up the things so they'll cancel. So I don't do a lot of checking with cubes because cubes you don't get primes and they all factor the same, and I get pretty good at these. For 14, I need the cube root of 125, so second square root 125. The cube root of 125 is 5. So my first piece is going to be 5x times 5x times 5x. I need to combine the 5 and the x together because 5 times 5 times 5 is 125. X times x times x is x cubed. And then I'll do the cube root of 64, which is 4. So now I know what goes in my parentheses, and I know the signs. First parentheses, same sign as a minus is a minus. Second parentheses, opposite of minus is a plus, and then a plus. First parentheses, one of each, which is a 5x and a 4. Second parentheses, first pair is 5x times 5x. Second parentheses is 5x times 4. Third in the second parentheses is 4 times 4. I leave the first parentheses how it is and get 5x minus 4, and then 5x times 5x is 25x squared. 5x times 4 is plus 20x. 4 times 4 is plus 16. Really the only thing I can blow sometimes on these is the signs, because it's easy for me to fill up the parentheses. It's actually kind of easy for me to get the signs. 16 and 14 should be just about the same because they both have 125x cubed and 64. The only difference between 14 and 16 are the signs. And the signs in this one, first you write the same sign, the opposite of the original sign, and then a plus. So it's same sign as plus, opposite of plus is minus, and then a plus. And then I'll just steal from here. First parentheses, one of each. Second parentheses is just going to be those again, and so I'm going to be lazy and just copy. Because if you have the same contents that you're factoring, the same cubes that you're factoring, then the only differences are going to be how the signs lay out. And if you multiply these out, they both would come out to where they needed to come out to be. $18, I'm going to call 64x cubed 4x times 4x times 4x. And 27, I'm going to call 3 times 3 times 3. Signs, first parentheses gets the same sign, which is a minus. Second parentheses gets the opposite of minus, which is plus, and then a plus. First parentheses, one of each, a 4x and a 3. Second parentheses, first pair goes first, which is 4x times 4x. Second parentheses goes second, which is 4x times 3. Last parentheses goes third, which is 3 times 3. I leave the first parentheses alone, leaving it 4x minus 3. And then second parentheses, I multiply the 4's and the x's and get 16x squared first. The middle I get a 12x, the last I get a 9. There's no common factors in these unless the original problem has a common factor. The parentheses won't have a common factor. Oh, and the second parentheses is always prime. It's a trinomial, but it's never ever going to be factorable. Probably should have said that a little bit earlier. Just came to my mind right now. 20. This is 3x times 3x times 3x and y times y times y. The signs are same sign as minus, which is a minus, opposite of minus, which is a plus, and then the last is always a plus. First parentheses, one of each, 1 3x and 1 y. Second parentheses, the first pair is 3x times 3x. Second pair is 3x times y. Last pair is y times y. So I really like these because they're just so repetitive. Once you get the template for the signs and write your cubes, it just falls apart. So my answer is going to be 3x minus y first. Second, 3x times 3x is 9x squared. 3x times y, I'm just going to leave that as 3xy. And y times y, I'm going to write as y squared. So it's 3x minus y, and then 9x squared plus 3xy plus y squared. For the exponents that aren't 3, you have to divide the exponent by 3. So for the y to the 6th, I'm going to divide its exponent by 3, and that's going to give me 3y squareds. So I'm going to go y squared, y squared, y squared, and x, x, x for my cubes. Signs go first, minus, which is the same sign as a minus, and then the opposite of a minus, and then a plus. First parentheses, one of each, a y squared minus x. Second parentheses, first pair, y squared times y squared. Second pair, y squared times x. Third pair, x times x. I leave the first parentheses alone at y squared minus x. The second parentheses, y squared times y squared, I add the exponents and get y to the 4th. In the middle, if you want to write these alphabetically, it's probably better, but if you left it y squared x, it's hardly wrong. It's just more common to write letters alphabetically. And then my last x times x is x squared, and that's done. In 24, 4 times 4 times 4 is 64. On the x, I divide its exponent by 3 and get an x squared. So the first piece is going to be 4x squared times 4x squared times 4x squared, and 1 is 1 times 1 times 1. So that's writing it as cubes, because 4x squared times 4x squared times 4x squared will multiply to 64x to the 6th, and 1 times 1 times 1 will multiply to be 1. Get my signs, minus first, plus and plus second. First parentheses, one of each. Ooh, this is a trick. 4x squared minus 1. Oh, this is a problem that could be a square and a cube. I said I wouldn't give one of these, but I did. I'm doing it, and I'll show you the trick. Wouldn't do these on a test, but it snuck in here. I'll live with it. Second parentheses, 4x squared times 4x squared, and then 4x squared times 1, and then 1 times 1. So this is 4x squared minus 1, and then that multiplies to be 16x to the 4th. That multiplies to be 4x squared. That multiplies to be 1. If you look at this problem, 64x to the 6th minus 1, it's both a cube problem and it's a square problem, because it could be written as 8x cubed times 8x cubed and 1 times 1. So it's a combination. You can think of it as a square because the numbers have square roots and the exponent's a multiple of 2. You can think of it as a cube because the numbers have cube roots and they're multiples of 3. These problems are the only kind you get the double factoring, and the trick to finishing this properly, so this is an okay answer, but that first parenthesis is a difference of squares, and that 4x squared minus 1 factors into 2x plus 1 and 2x minus 1, and this would be the best answer. So sometimes problems that are combination problems, cubes and squares, I usually treat them as a cube first, and then the square part will come out in the first parentheses, and you can factor the first parentheses as a difference of squares. So this would be the best answer. Never would do that on a test to you. I didn't even realize I did it in the homework. For 26, 8 is 2 times 2 times 2. For the x, I need to divide the exponent by 3. So for the x, I go 9 over 3 and get x cubed. For the first piece, I'm going to consider it as 2x times 2x times 2x. And the y cubed is y times y times y. Template my signs. Minus is the same sign as the original problem. Then the opposite of minus is plus. The last is always plus. First parentheses, 1 of each. Second parentheses, first pair is 2x times 2x. Second pair is 2x times y. Last pair is y times y. And so my answer, first parentheses, I'm going to leave 2x minus y. 2x times 2x in the second parentheses gives me 4x squared. 2x times y in the second parentheses gives me 2xy. And y times y in the second parentheses gives me y squared. Second parentheses is always prime. Sometimes that first parentheses sneaks up on you in factors because the original problem was like a hybrid problem. 28, there's a common factor that you have to factor out first. That common factor is a 3. That 3 that's a common factor is going to be part of my answer, but it's not going to be part of the double parentheses. So when I go to write my answer for this, I'm going to make a template for the x cubed minus 27. I'm going to bring the 3 down, and I'm going to factor the x cubed minus 27 by writing what makes it cubes. X is a cube because it's x times x times x. 27 is 3 times 3 times 3. First parentheses, 1 of each. Second parentheses, first pair is x times x. Second pair is x times 3. Last pair is 3 times 3. My answer is going to have that common factor of 3, then the x minus 3, and then I'll start multiplying. X times x is x squared. X times 3 is 3x. 3 times 3 is 9. I imagine I have a few more common factor ones coming, and that's going to be the only twist to these next few problems. So how far did we go? We're getting too far. 42 we end at. So we've got another 6 problems to do or so. They all probably will have common factors. 30 has a common factor of a 2. When I factor out the 2, I divide the numbers by 2. I'll be left with an x cubed plus 64. That 2 is going to be part of my answer, and the x cubed plus 64, I'll template for it, putting the signs in. The same sign as plus is plus, opposite of plus is minus, and then the plus. The x cubed plus 64 is a cube because it's xxx and 444. First parentheses, 1 of each. Second parentheses, first pair is x times x. Second pair is x times 4. Third pair is 4 times 4. And for an answer, I get 2 times x plus 4, and then x squared minus 4x plus 16. 32, there's also a common factor. It's a common factor of a y. I'm going to factor out a y. That's going to leave me 3 y's and then just a 64. The y's going to stick around. The y cubed minus 64 is going to be broken up into 2 parentheses. Same sign of minus is minus, then the opposite of minus, and then a plus. Y cubed minus 64 is y, and 4, 4, 4. First parentheses, 1 of each, which is a y and a 4. Looks like a y and a y almost. Second parentheses, a y and a y and a 4, and a 4 and a 4. So my answer is going to be y times y minus 4. Then y times y, I'm going to write y squared. Y times 4, I'm going to write 4y. And then 4 times 4, I'm going to write 16. Haven't been checking these because they're a nuisance to check. So there could be some mistakes that I've made just because I make mistakes. And if you catch a mistake, let me know so I can let everybody know that, hey, when I was doing problem 18, I should have done this, but I did this. So lots more common factors. Ooh, I know there's a common factor of a y. I think there's a common factor of a 3. I'm going to gamble by writing a 3y. The first piece, I get rid of the 3. I'm left with 3 y's. The second piece, I have to be able to divide 192 divided by 3. And 192 divided by 3 is 64. That's a good thing. So when I factor out a 3y, I divide the number by 3. I take a y away. And I took that y away, and I divided that into a 64. So this is a y, 4, 4, 4. I leave the 3y. My template is a minus, a plus, and a plus. First parentheses, 1 of each with a y and a 4. Second parentheses, first pair is y times y. Second parentheses is y times 4. Third parentheses is 4 times 4. Gives 3y times y minus 4. And then y times y is y squared. Y times 4 is plus 4y. 4 times 4 is 16. And I'm done. Second parentheses is always prime. First parentheses might factor if the original problem was also a square and a cube simultaneously. I think my factor is going to be 3. I take the smaller exponent on the x, so I think it's going to be 3x squared for my common factor. For the first one, I factored out the 3. I took away 2 of the 5 x's. I'm left with 3 x's. And for the second one, I go 375 divided by 3, and I get 125. And I took its 2 x's away. So now I'm going to template. X cubed is x times x times x. 125 is 5 times 5 times 5. My signs are minus, plus, plus. First parentheses, 1 of each. Second parentheses, couple of x's. An x and a 5. And a couple of 5's. My answer is going to be 3x squared times x minus 5, and then second parentheses gives me an x squared plus 5x plus 25. 3 more, I think. And so hopefully you're feeling good about these, and maybe that you don't even feel the need to watch the rest of the video. They're very repetitive factoring the cubes, other than factoring out common factors. No common factors on the next 2. They're written in an odd order, but I'm going to leave them because the letters are written second. That looks odd to me, but since they're written that way, I'm going to leave them that way. So for 38, I'm going to make 64 as 4 times 4 times 4. Y cubed is y times y times y. Signs are minus, plus, and plus. First parentheses, 1 of each in the order that they come, so 1, 4, and 1 y. Second parentheses, start pairing. 4 times 4. 4 times y. Y times y. So I get 4 minus y. Then the 4 times 4 is 16. The 4 times y is 4y. The y times y is y squared. That's it. 40. It's 5 times 5 times 5, and 2x times 2x times 2x. Template. First parentheses gets a plus sign. Second parentheses, opposite of plus, which is minus, and the last is always plus. First parentheses, one of each in the order that they come, a 5 and a 2x. Second parentheses, 5 times 5, 5 times 2x, 2x times 2x. So I'm going to get 5 plus 2x, and then 25 minus 10x plus 4x squared. Even though that's written in a kind of a bad order with the letters written second and the numbers without the letters written first, I'm just going to leave it that way because the problems were given to me that way. I don't feel bad about writing things in an awkward order if the original problem is already also in an awkward order. Last one, I hope. Yes. Last one. 64 is 4 times 4 times 4. And for the x, I divide its exponent by 3 and get an x cubed. So it's going to be an x cubed, x cubed, x cubed. Template for the signs, get the same sign as the problem. The problem has a plus sign, the same sign of plus is plus. And then the opposite sign from the original problem, the opposite of plus is minus. And then the last sign is always plus. First parentheses, one of each, meaning 1 4 and 1 x cubed. Again, it looks odd in that order, but I'm going to leave it in that order. Second parentheses, first pair is 4 times 4. Second parentheses is 4 times x cubed. Third parentheses is x cubed times x cubed. Leave the first parentheses at 4 plus x cubed. 4 times 4 in the second parentheses is 16. 4 times x cubed I'm going to leave as 4 times x cubed. And for the x's, x cubed times x cubed is x to the 6. I add their exponents. And that's the answer. Again, it's written in an odd order, but I can certainly leave it in that order because the original problem was written in that same awkward order. So that's everything that I can do for factoring. The next section, it's going to scramble all the problems from the first 6 sections. I think it's 6 sections. I think this was 1/6. And this is where the challenge is going to be. Even if you feel real comfortable factoring the problems within the section, when we scramble the problems, sometimes it's hard to know what strategy that you need to use to factor. And that's what I need to do really well when I lecture tomorrow. I need to really help you be able to look at a problem to classify what factoring strategy to use, because that's going to be the difference between you really being good at factoring on the test and being kind of so-so on the test. Just being able to look at a problem and know the factoring strategy, because we've learned strategies for squares, cubes, we learned grouping for 4 terms, we learned bottoms up and some other method for factoring with 3 terms, and we have to remember all of those and know when to use which strategy, and that's the trick that we need to master that.